everybody, I'm back, and it's been a really long time since I last released a video, and I'm really quite terribly sorry about that. Finding a work-life balance and maintaining YouTube has been really challenging, but I promise I'm going to start trying to get better about that. I know I promised that in other videos that I've made that I'll probably actually release after this, because I've got a backlog of videos. I've got something like 25 videos of a special series that I need to edit and upload and start releasing. But I wanted to do something simple-ish while also completing a project for work that I promised I'd have done for tomorrow. So gonna kill two birds with one stone here. We'll do a new video, and I'll show you some neat stuff that I've learned. So we've got a spot in the back shelves of our work that's a little dark, so I volunteered to make some lights for it. So I'm going to use two of these leftover cobs that I have from my workbench lighting, and we're going to build a quick little constant current circuit to run these LEDs. It's always a really good idea to use a constant current driver for an LED rather than a constant voltage driver. And I'll explain why if one of these LEDs does, I can't remember if one of these is one of the defective LEDs or not, but they'll do well enough for the purposes that we'll be needing for work. So I have some components here. I've got my LED cobs. I've got this big chunky leftover power supply that we had in a box somewhere at work. This is called a linear power supply, which means it's got a transformer and a rectifier and a bunch of other linear components to turn the alternating current into direct current, rather than the more complicated and also more efficient switching power supplies that are much more common today. So I'm going to start by explaining what I've got here. This is a MOSFET. Specifically, it is an N-channel power MOSFET, which can handle, I think this particular one can handle up to 75 amps? I don't honestly remember. Anyway, it's kind of a magical little device that I didn't learn a great deal about, but it's a transistor, but instead of using current on its base, which is actually called the gate on a MOSFET, it uses voltage to control the current through the other legs of the component here. So we're going to use this, we're going to use this as the valve for our current. We're going to control our current flow through this MOSFET here. And to keep that current constant, we're going to use a sense resistor, which actually I don't need. Why do I have this? I don't need this one. Go over there. We're going to need a sense resistor that's going to basically determine how much current we want to be going through this MOSFET. That's going to be connected to the base of this transistor. This is just a small transistor. It doesn't have to handle a huge amount of current. And this transistor, when that sense resistor sees that there's too much current going through it, it's going to pull the gate of this to ground, which will start turning this off. And then there'll sort of be this constant push-pulling until a median is reached and a constant current is flowing through the LEDs. This is important because the current and voltage drain of an LED changes as it heats up. So we need to have something that's going to adjust on the fly. Now, for my workbench lights, I'm using a little trick with an LM317. I'll do a video on that at some point. But for this one, this circuit is actually, I came up with this one after doing some research on MOSFETs. This circuit is a whole heck of a lot more efficient than the LM317 circuit that I used up there. So I'm just going to quickly sketch out what this circuit looks like. And then we'll talk a little bit more. I'll show a little bit more on the actual diagram how this circuit is going to work. So we're going to start with our positive rail here, and we're going to take it out a little bit, and then we're going to pull down to a resistor here. And this resistor doesn't have to be any particular value. A higher value means that when it's in complete cutoff situation, which will never happen, hopefully, that you don't have a lot of current flowing through the currents. Well, I guess I'll call it the sense transistor, because it's not meant for a lot of current, so you want to kind of control that. So I picked 100k ohms, just an arbitrary value there. Doesn't really matter as long as it's a higher value. Then we're going to continue coming out of the positive rail, and we're going to come into our LED bar. I'm not going to bother by drawing all 144 LEDs, so I'm just going to draw a single LED here that's going to represent these bars. And that's going to come down. Now, this resistor is going to be activating this MOSFET. Now, MOSFETs have a really, really complicated official symbol that looks like this. It's like that, and then like that, and then like that, and like that. And then this comes down and goes out. And then there's like a little Zener diode symbol here that goes like that. And then this comes out, and this comes down off of here and goes on to there, and that comes out, and then this goes over here, and then that goes over like that, and then there's an arrow that's pointing inwards there, and then you put a big circle around the whole mess. That's the official symbol for a MOSFET. That is a pain in the butt to draw, or in this case, this is the official symbol for an N-channel MOSFET. That's a pain in the butt to draw, so we're going to go with what is accepted as the more simple version of the symbol, and we're just going to go like this, and like this, and like, I didn't really do my spacing very well on this one, but then that, and like that, and then like this, like that, and like that. Well, I guess we'll bring this one down like that, and then you put a circle around that whole thing. That's a simplified version of a N-channel MOSFET. It's a lot easier to draw, but it's not really true to the symbology of the MOSFET, but we're going to go with that for now. Now, a transistor normally has an emitter, a collector, and a base. Now, these guys have something different. They have a gate, a drain, and a source. Now, the reason why the drain is where the positive voltage is and the source is where the negative is because of electron current flow instead of conventional current flow. Now, I'm going to go into more detail with that in another video, but basically current actually flows from negative to positive because the electron is the current carrier and it is a negatively charged particle. So it will actually be coming up through the source and out through the drain, but that's complicated stuff for later, so we're not going to worry about that. Anyway, so then it's going to come out here, and it's going to come through a pair of resistors, and I'll explain the math that I picked for those resistors a little bit later. I really am not drawing this very well, and this is going to be our negative rail. Now, from the top of these resistors, we're going to need to come out here to about here, and we're going to be coming into the base of a transistor, this transistor here, and he's going to be like this, and like that, and like this, and like that, and then he's coming out to ground there. And then this is going to be the base, this is going to be the collector, that's going to be the emitter. So the calculation for determining what we need for the current here, this is going to be R2, this entire section here, and this is R1 up here. We'll call this one Q1, and this is going to be Q2, but we don't really need to worry about the Q's, we just need R1 and R2. So R2 is going to be equal to VBE, which ostensibly is between 0.5 to 0.7 volts. I went with 0.5 when I was doing my calculations for the components on this one because it made the math a little nicer. Now, that's the voltage over the current of the LED. Now, each of these LEDs ostensibly runs at about 500-ish milliamps, and you can calculate that P equals IV. We know these are 6-watt LEDs, so power is 6 watts equals the current times the voltage, which in this case they're 12-volt strips. You divide by 12 on that side, you divide by 12 on this side, and you get 0.5 equals I, or 500 milliamps. Oops, 500 milliamps. Oh, I'm just batting 1,000 tonight. Anyway, so that's we're calculating for 500 milliamps, so that's going to be our maximum current or our minimum resistance. So we take 0.5 and we divide by, oh, and that's per bar. So we need to take 500 milliamps twice, and we're going to have 1 amp. Divide that out, and we get the R equaling 0.5 ohms. Oh, I should probably mute my computer. Oh well. Anyway, 0.5 ohms, that's for our minimum current. Now, that 0.5 ohms, we're going to be dissipating 1 amp through... Hang on a moment, I'm going to be right back. Sorry, needed to mute my computer. I was getting a stream of messages. Anyway, so now we need to figure out the current or the power that's being dissipated by the resistor here. So we're going to go back to P equals IV. We've got the fact that we're dissipating 1 amp through those resistors, and they are going to be running at 0.5 volts, so we've got 1 times point, because P equals 1 amp I times the voltage, which is 0.5, which is the voltage we're running off here. So power equals 0.5 watts. So we want to have a fairly beefy resistor, a half-watt resistor. These are actually 1-watt resistors that I'm going to be putting in parallel to make the half-ohm resistance, because these are 1-ohm resistors. But when you're running a resistor at its rated wattage, it's going to heat up to about 100 degrees Celsius, because that's its operating temperature at its rated wattage. I don't want a resistor at 100 degrees Celsius sitting there on the board that's running this LED, so I'm using 2 1-watt resistors in parallel, which is going to make their rating basically 2 watts, and they'll stay nice and cool for the running of the lights. Anyway, so then we're going to take a this little guy here. That's a 500 ohm 0.5 ohms, 500 ohm. This is a 500 ohm potentiometer, which we're going to use in this case as a rheostat, and adjusting this will make the lights brighter and dimmer. The reason I want to use this is to find a nice brightness for the LEDs in that section of the shelving, and hopefully run them at a little less than their 500 milliamps, because again, that's driving these LEDs at their rated current, and if we run them under that rating, they'll last longer. So we're going to take that 500 ohm potentiometer, put it in series with this resistor, so that we have, when this goes down to 0, we still have some current sensing in those resistors. And I'm going to throw a switch in somewhere over here, perhaps, to turn it on and off. Anyway, so that's what we're going to do. and I'm actually going to solder this one on to a little piece of breadboard here. This is a nice visual representation actually for how the tracks work in a breadboard, where you have the rows of 5 all connected in a horizontal row, and then you have bus bars. They're normally down the sides, but on this one they're down the middle. And so we're going to solder the circuit together on this, and then we'll be ready to go. So I'm going to go ahead and solder this in time-lapse mode because I have rambled on long enough. I've probably made you all bored to tears. So let's put this circuit together, and I'll see you on the other side of the time-lapse. Alright, and we're back. I hope you guys weren't following my soldering too closely, because I actually messed up on where I soldered the LEDs. Everything else was fine. I just was, I think I was thinking too hard about the way I used to do it with the LM317s, and I soldered the leads of the LED into the wrong place. But after brief troubleshooting, I got it figured out. So, we're going to go ahead and power up the circuit, and you'll notice how the LEDs are really quite dim. And that's because when this resistor is maxed out, they're running at about, I think it's about 800 microamps. So there's not a lot of oomph going through those guys. So we're going to take this funny looking little tool here. This is called a pot trimmer. Now, that has nothing to do with cannabis, but everything to do with trimming a potentiometer. And it's got a little spade on this end, and this is actually meant for the potentiometers that have just a little screw on them that's inset inside the potentiometer, like these guys here, which you can't see, but well, I guess I'll temporarily disconnect one of these. So, the heatsink came loose. But anyway, you'll see this potentiometer, it's got a little spade, or a little slot there, and I can go in and adjust it with that spade. But for the type of potentiometer, give me a second here to reconnect this light. For the type of potentiometer I'm using for this, it's got a little brass screw there that's sticking up, and that's what this inset spade lug or little spade there is for, and that just kind of sockets on over top of that brass screw and makes it so that the screwdriver doesn't, or the pot trimmer does, well, I guess it's kind of a screwdriver, but not really. The pot trimmer doesn't slide off of the little screw while you're adjusting it. Now this is a multi-turn potentiometer, which means it gives us fairly fine control over the brightness of these LEDs. You'll notice they're getting very gradually brighter now, and then they get brighter and brighter and brighter and brighter and brighter until they're running at their maximum brightness there. So we'll just tank back on that just a little bit here. And there we have a successful constant current circuit for these LEDs. Now, I was going to talk a little bit about why we use a constant current circuit, but none of these LEDs has actually failed. On some of my other ones, when you have them dimmed down like this, in fact, that's actually really uniform brightness, which means these are very nicely matched circuit or cobs here. But you might notice that one of those LEDs might go out. Now, an LED, when they fail, they typically fail short circuit, which means that LED goes away and it looks like just a 0 ohm resistor. Now, because of that, the forward drop of that LED has gone away. If you're running a constant voltage circuit, that means that the rest of these LEDs will start to pull more current. And then that makes them fail faster, and then another one fails and they pull more current, and then another one fails and then they pull more current, and you end up with a cascade failure, and they eventually all die. When you run it like this, if one of these LEDs fails, this circuit clamps down on the current that's going through there and keeps them all at a static current load, and they don't kill themselves if one dies. It just clamps down on the circuit, the LEDs receive the current that they're supposed to receive, and the circuit continues functioning normally. Anyway, so that's a quick introduction into the realm of a constant current LED driver using a MOSFET and 2 LED bars. Thanks for joining me. I hope to release videos on a slightly more constant basis. I'm not going to inundate you all in the new series that I've got running. I'm going to try to have a couple of regular, normal videos here and there interspersed amongst the other series. So thanks for joining me. We'll see you all in the next video. Bye-bye.